good evening to all. I'm deeply honored to have been asked to talk here because I thought before coming that my reputation outside France was a good illustration of the absolute zero. So tonight I'm going to try to give you a couple hints on what it means to get fossil-free also. When you say fossil-free to a number of people in the general public, they might understand some things that you might also understand, maybe. Might be this: if you're fossil-free, you shouldn't go to the museum, or you should not be allowed to pick up a fossil on the beach, or you should live in a world with no old-timer, or, that's a drama, you cannot shop. Actually, what I'm going to talk about is this, and you'll see that it's faster said than done. I've been downsized. I thought I should talk for 1 hour. I've just learned that I should talk for 45 minutes. So I'm going to do something which is very useful when there is a risk of downsizing. And actually, I know myself, I know I'm too talkative, so I'm going to begin by the conclusions. So you'll be sure to have them. The first conclusion I'm going to defend is that GDP growth for the last 2 centuries is basically energy, then energy, then energy, and some geniuses and marvelous engineers that we have known have just used what Mother Nature has put at our disposal, which is oil, gas, coal, and some minor other things. The second thing that I'm going to show you is that what counts regarding energy is the size, just like for some other topics. And that price is not an issue, and you might say that price and volumes are related. No, you will see that it's not the case. Some other thing that I'm going to explain is that in Europe, the energy supply is already constrained to decrease, and that has triggered the kind of, what do you say, millennial slowdown, or millennial recession, or millennial stagnation, or whatever. I'm also going to explain is that phasing out fossil fuels deliberately is a better bargain than just waiting for the job to be done by whatever cause we are not mastering. What I'm also going to say is that there is no silver bullet regarding technology. No technological improvement will go fast enough to relieve us from deliberate efforts regarding behavior. The other thing that I'm going to say also, which is I understand in this country something heretic, is that free market is something that doesn't help when you look at long-term investments. Another conclusion that I'm going to defend is that we are in such a position that we must turn something which is adverse into an opportunity. When you are back to the wall, your best buy is to take advantage of the fact that you will have to address the constraint and try to take some kind of advantage out of it. But it requires something which actually is probably better done on this side of the channel than on the other side of the channel, which is to put back, because there was a time where it was used very, very common, to put back more science into politics. If you try to elaborate plans that violate the rule of 3, they will fail no matter what. And we've been tried this kind of thing a number of times recently. It requires to be more economically sound about environmental solutions. If we are only sentimental, most plans will fail also. And it will require to shift from more investment and less consumption into the GDP. Basically, we'll have to work more to earn less, kind of. Now, let's go back to the beginning. You know him. He's probably the best-known professor in UK. His equivalent in France is the best-known professor in France. When he asks a question, you are sure that 8 million people know the answer 10 minutes later. Probably the same here. As you probably know also, if you watch this emission, when this very, very well-known professor asks a question, generally you know the 4 possible answers in advance. Here I'm going to cheat, I won't give you the answers in advance. So, I'm just asking you the question, what do you think energy is? If you go out in the street and ask the question to the general public, I'm ready to bet that the first answer you'll get is this one. Energy is a bill. Okay? I have to pay my electricity, I have to pay my gas. If the person you're asking the question to is very sound, is going to answer, I have to pay my gasoline. It's not always something automatic with a number of people, but basically energy equals a bill. You have another fraction of the population, a smaller fraction, in which the reflex when you say energy is saving. Okay? Energy equals savings. You don't know why, you don't know what, you don't know necessarily what precise, etc., but savings. And then you can ask the question to a poet, and the poet will answer this. Energy is what I'm packed with a morning when I feel that I'm going to eat the world. Well, actually, the poet is the closest to the truth. Because energy, as you might remember for some of you, in physics, is by definition what needs change. So if you have energy, you have the power to change things. If you have the power to change things, it means that you have energy. Basically, we're talking about the same things. Energy equals change. So when you count energy, before counting energy in pounds or in euros or in whatever you want, you should count, or we must count, energy with the unit that characterizes physical change, that is joules or kilowatt hours. There are a number of situations that I'm now going to show, in which obviously energy means change. For example, when a temperature changes somewhere, you have energy involved. When a speed changes somewhere, you have energy involved. When a shape changes somewhere, you have energy involved. When a chemical composition changes somewhere, you have energy involved, etc., etc., etc. This is particularly delightful in summer. So whenever you have a physical change or a chemical change or a change whatsoever in the world that surrounds us, you have energy involved. So again, using energy and changing the world is exactly the same thing. Exactly the same thing. And from there, the first conclusions that I'm going to suggest is that green energy doesn't exist. You know, green energy is some energy that you could use with no side effects. But if you have no side effects, it means that you have no effects at all. Because whenever you have some kind of effect, you have some kind of side effect. So green energy doesn't exist. When you look at figures, you realize that basically green energy is energy which is used in such small quantities that it cannot have significant side effects or adverse side effects. But then it also means that it doesn't have positive significant effects. So green energy doesn't exist, as pink energy doesn't exist, as silver energy doesn't exist. Basically, you have energy or you don't have energy. If you have energy, you have the power of change. If you don't have energy, you don't have the power of change. If you trigger significant change, you trigger significant positive and negative effects. Basically. I'm now going to show you a little calculation which is at the root of everything that will follow, for it will try to show you that the figures regarding the energy we use today are huge compared to what happened to our species in historical times. This is some activities that some of you may have performed. Consists of putting on a backpack and climbing up the mountain. It's easier, I was about to say it's easier to do if you're in France, but no. Suppose you climb the hills up in the northern part of Great Britain. If you weigh 80 kilograms and put on a backpack which weighs 10 kilograms and climb 2,000 meters high, has anyone in the room already climbed 2,000 meters in a day? One. It's a good exercise. Advise you to do it, it's a good exercise. Well, if you do that, the mechanical energy that your legs will provide is a ridiculous half a kilowatt hour. Okay, so put on a backpack, sweat for a day, half a kilowatt hour is all you get from your legs. If you dig a big hole, if you do that 1 day out of 2, which is a good exercise, then at the end of the year, your body will have been able to provide 100 kilowatt hour of mechanical energy. Okay, so use your legs all year round. All you can do is provide 100 kilowatt hours of mechanical energy. If you dig a big hole and shovel, say, 6 cubic meters of earth, which means roughly 15 tons of earth, up 1 meter. Who has done that already? Good. 15 tons?
50.
In a day?
Not a day.
Ah, okay. Well, in a day, the mechanical output you will have performed is 10 times less. 0.05 kilowatt hour is all your arms and back will be able to provide. Do that 1 day out of 2, it's 10 kilowatt hours at the end of the year. So basically, a man at work, heavy duty work, will be able to provide in a year 10 to 100 kilowatt hours of mechanical energy. Well, it happens that 10 kilowatt hours is basically what you get when you burn 1 liter of gasoline. 1 liter of gasoline that a standard Western country inhabitant will use 1,500 liters in a year. 1 liter of gasoline, when it burns, gives you 10 kilowatt hours of heat. And if you put that into an engine, you will get 2 to 4 kilowatt hours of mechanical output from it. Meaning that in 1 single liter of gasoline, you have the same ability to change the environment that in 10 to 100 days of work of a human body. 1 liter of gasoline, 10 to 100 slaves working for a full day. Now let's talk money. Suppose you pay your employee performing some kind of physical work at the French minimum wage. French minimum wage is around 1,000 euros per month. I'm sorry, I'm not going to convert euros into pounds, but it's basically a 1-to-1 ratio for what will follow. I mean, you'll get the correct order of magnitude. We're not in the city here. So if I pay my worker 1,000 euros per month, then I will pay my kilowatt hour several hundred to several thousand euros, when the machine using gasoline will give me the same service at the marginal cost of a couple tens of cents per kilowatt hour. Meaning that when I go from the machine to a human body, the cost of transforming the environment is multiplied by a couple hundred to a couple thousands. All the history of the 19th and the 20th century lie in these figures. All. This explains the tremendous increase in the productivity of work, the tremendous decrease of the unitary cost of production, the tremendous increase in the consumption of material goods and services. Everything. Everything lies within this figure. Now I'm going to do something which is politically totally incorrect. I'm going to take a slave. You know that generally a slave, except for some people going to some places that I won't name, slaves don't want to be slaves. So you have to go and get them, or you have to pay someone to go and get them, and then you have to pay to prevent the slave from escaping, and you have to feed him and prevent him from dying of cold, heat, etc., etc. Well, if you perform the calculation of what it costs you to go and get the slave and prevent the slave from dying, you will realize that the mechanical output coming from the slave still costs you 10 to 100 times what comes from the machine. I draw the conclusion from this figure that if slavery has disappeared in the world, or almost disappeared in the world, it's not because our genetic code has changed over 2 centuries. I believe that our genetic code is strictly the same today than what it was 2 centuries ago. I believe that it's just of no use going to get slaves when the machine that doesn't go on strike, that never sleeps and that doesn't revolt, can perform the same service for 10 to 100 times less money. So basically slavery has disappeared because of oil, gas, coal, and various little things that go after. So we have come from this, which is fully immoral, not very efficient, but fully renewable. And that was performing some kind of ridiculous power to machines that are fully efficient, fully moral, but unfortunately for us, running on perfectly non-renewable energy. Say, for example, take a car or take a tractor, where a car or a tractor has the mechanical power of 100 pair of legs, of several hundred pairs of legs, or several tens pairs of horses' legs. So if you put a tractor into a field, you can at the same time remove from the field several hundreds of peasants that can become factory workers, then white collars. I will show you afterwards, but it's exactly the way it has evolved in Western countries. Take one of these machines which is used in public works. Well, one of these machines can replace several thousands pairs of arms. If today in London construction was to be performed with only arms and legs, and people pulling up stones with ropes and bringing stones into the center of the city on small carriages pulled by horses, well, I think that you could multiply by 100 the time required to build anything. And when I say 100, I'm conservative. Take a truck, a lorry. Well, it has the same mechanical power that several thousand times the legs of the driver. Take a train, like the Eurostar, that was late, that brought me this morning. Well, the Eurostar has the same power that 100,000 times that of the driver's legs. A plane has the same power than 1,000,000 times that of the pilot's legs. And by the way, a jet plane, modern jet plane, has the same power than a steel mill. Basically. If steel mills, if we didn't have energy to perform the same amount of work than a steel mill, well, all the greater Paris should be put at work with hammers and hammer steel all day long. 10 million people. One steel mill. And the number of people which is required to drive a steel mill is one. Well, actually, you have plenty of people around for maintenance, etc. But at a given time, in the cabin, which pilots the mill, you have one person. One person. One person. Commanding the equivalent of 10 million people. So we never had so many slaves and workers. Only they are machines. Only they are machines. And these machines, they eat energy. Actually, when we say that humans consume energy, it's false. You don't consume energy. You don't eat coal. Well, you don't drink oil. I don't advise that you do so. And you don't put directly your fingers into the socket. I definitely do not advise that you do so. When we say that we use energy, actually what we do is that we feed machines with energy and we get the service out of it. This is expressed in kilowatt hours per year, the average energy, in quotes, consumption per human being on Earth for over a century and a half. So what you can see on this graph is that our great ancestors, 1 century and a half ago, here, they used about 1,500 kilowatt hours per year, and this energy basically fed machines that provided heat, stoves, and the first steam machines that were used for the first steamboats, first trains, first mills, etc. It was about 50-50 wood and coal. And then what you can see is that the amount of coal per capita rises, then remains constant for about 1 century, then begins to rise again. And this is the amount of coal per capita. In the same time, of course, the population increases, which means that the amount of coal used on Earth has never decreased since we have begun to use coal. It has always risen. And the reason for this is that today, 2/3 of the coal extracted from mines ends in a power plant. Coal is by far, I will show you after, the first way to produce electricity on Earth, by far. What you can see then is that the other forms of energy got piled up on top of the previous ones. There has been no major replacement of one form of energy by another over the last century and a half. Never, ever. Oil came on top of coal because oil is not used at all for the same type of services than coal. Oil basically feeds machines that provide movement, or actually motion. 98% of what flies or navigates or drives on Earth is moved by oil. So oil is by essence the energy of mobility, and by essence the energy of globalization. Then gas came on top of oil, hydro and nuclear came on top, etc. And what you can see here is all that gets journalists crazy. So it's the sum of wind, solar, biogas, geothermal, tidal, whatever. I mean, all new renewable energy. When you look at the supply per capita in the world, that's what it represents here. What you can see on this graph is that over that century and a half, we had two very distinct periods. The first one goes from the beginning of that series to the oil shocks. And you see that during that period, the energy supply per capita increases over 2% per year. It means that each individual has the ability each year to create 2.5% of physical flows more than the previous year. So each year, technical and at constant level of technique, I would say, any individual has the possibility to manufacture 2.5% additional table, chairs, square meters of housing, cars, etc. What this means basically is that the productivity per worker increases at least 2.5% per year. And the consumption per capita of any good or service increases at least 2.5% per year. And what we know in France as the 30 Glorious, which are here, correspond to a particularly steep rise in the energy use per capita. And you see that after the oil shock, we lose an order of magnitude. The rise of the energy consumption per capita in average, goes down to point-something% per year. But if you look at OECD countries, what we generally call rich countries, Western Europe, Northern America, Australia, Japan, Southern Korea, then the rise between the oil shocks and today is exactly zero. The oil shocks correspond to something which has not been noticed by the economists, which is that the energy consumption per capita stopped rising. What the economists generally see is that the price went up, then down, then it's over. It's not over at all. It's the end of the energy rise per capita. When did all the problems that we have today begin? Unemployment, rising debt. They all began in the oil shock, during the oil shocks. All. And ever since then, we have been unable to master them, because ever since then, every year we have thought that growth would resume the next year. So we have maintained a system of spending which was based on income increasing 3% per year, because energy was increasing 3% per year, and that system never came back. And so the way we have tried to fix the problem is with an increasing debt and leaving a fraction of people that would like to work on the side because there is not enough money to pay, as we did pay before, for everyone. Still, if we look at absolute figures, we are in a state which is unprecedented. When you look at absolute figures, the energy consumption per capita on average in the world is about 20,000 kilowatt hours per year. If I go back to my slave equivalent, it means that if we did not have on Earth oil and gas and coal and the minor other things, then to live the life we live today, we would need some additional planet with 1,400 billion people on it, cycling all day, and sending us the corresponding mechanical energy. In other words, the average Earth inhabitant today lives as if he or she had 200 slaves at his disposal, 24 hours a day, 365 days a year. That's for the average human being. But in Western countries, all these mechanical slaves eating their own food, they provide closer to 500 to 1,000 slaves per capita. So you and I, we live today just as if we had 500 to 1,000 slaves per capita. The more money you earn, the more slaves you have, basically. In a finite world, it's wonderful. In an infinite world, sorry, it's wonderful. The issues arise because we live in a finite world. Now I'm going to say heretic things regarding the economy. I know that London is the world leading place for economics. Well, bad luck, part of it is completely false. This is the economy we are today reasoning on. You have two production factors, work and capital. And if the GDP is not growing fast enough, and so we have issues with unemployment, pension funds, retirement, etc., and the national health system, well, we ask the bankers to stop playing at the roulette with their money and favor real investment. We ask the people that are lazy enough not to get up and to go to work. And then the GDP increases. Well, it's precisely what we've tried to do for the last 7 years. And when you look at figures for the whole Europe, you realize that it's not working. And it's not working because this is not the correct representation of the system. Here's the correct representation of the system. Any human production needs something which is very basic, but always forgotten, which is a resource to transform. All you can see in this room, absolutely all you can see in this room, with absolutely no exception, is natural resources that we have transformed through our activity. It's true for your clothing, it's true for the seats, it's true for the desks, it's true for the computer I'm using, it's true for the train that brought me in, it's true for any building that you will see outside. It's anything that you will see from the time you went up to the time you will go to bed, anything you will see from the time you were born to the time you will die, late enough, I wish you, is natural resources transformed by our activity. Anything. No natural resources, no production. No natural resources, no production. Why don't we see our natural resources in the economic equations? Just because the classical economists 2 centuries ago, when they began the theory, they say economics deals with what is rare. Natural resources are plentiful, so we will consider that they are free. It's exactly what they wrote 2 centuries ago. And as they wrote this 2 centuries ago, we kept the convention so far, even though the orders of magnitudes have completely changed. And it was a correct first order approximation 2 centuries ago, and today it's totally false. Totally false. So this is the way it works. And actually, capital is something which is produced exactly the same way that any other type of production. For example, this building is past resources and work. A patent is past resources and work. A software is past resources and work. A knowledge is past resources and work. So basically, any production is resources and work. Capital just has the property of not being destroyed when you use it. That's all. That's the sole difference. And work, which is transformation, is performed for 1 by our muscles and for 200 by machines using energy. And this simple diagram explains why. If you have a stress on energy in volume, you will have a stress on GDP in volume, no matter what. And if you have a stress on resources, you will also have a stress on production, even if you have plenty of capital and plenty of workers. Very simple. And now you understand why, from this, energy dominates by far. Today, it was not true 2 centuries ago again, but today, energy and machines dominate by far human muscles. And so, it's logical that the best macroeconomic model in the world is just a straight line. Just tell me how much energy you use, I will tell you how much GDP you have. It is very, very simple. Here you have dots that go from 1965, to 2013 upright. And for each dot, you have the energy consumption of the year, horizontal axis, and the world GDP in constant dollars, vertical axis. And what you can see is that basically you have the logical consequence of the diagram that you just had before. This is also a logical consequence of the diagram that you had before. On this graph, the green curve shows the variation year on year of the energy consumed in the world. And the brown curve shows you the annual variation year on year of the industrial output. Give me one, I will give you the other. Same for the GDP. Here you have the annual change year on year for the energy use in green and the annual change year on year for the world GDP in blue. So the best thing that you should look at if you want to know what the GDP is going to be is the energy consumption. It's the best early sign that you can get of what the GDP is going to be. Here's another curve which goes the same direction. You have here the world GDP since Mr. Jesus Christ was born, year 0, in the world. So you see that for 1 millennia, people that wanted to get elected had no issue with growth. There was no need to promise growth. There was no growth. There was no growth, no need to promise growth. And it's a big relief, well, there were no elections at that time also. There might be a link between the two. No, there might be a link between the two. Because when there is no growth, any promise of something additional you make to A goes along with something you have to withdraw from B. No growth. Okay? So you must promise at the same time, I will give you more, I will give you less. It's much easier when you say, I will give you more, I will give you more, when you get elected. So, 1,000 years without growth. To the beginning of the Industrial Revolution, the growth was so small that it was not worth talking about it. Then, fossil fuels come in. And then we have growth. 3% per year. Who in this room, looking at this graph, is ready to bet all his savings, the bet being forwarded to your heirs, that it's going to go on at 3% a year forever? Well, I take the bet with you.
I don't have any savings.
It's okay. I'm sure that if I look in one of your drawers, I will find £1. It's enough. I'm sure you will. So this is again a logical consequence of what I just explained. More and more machines put to work. Today, it's machines that produce for us. It's machines that produce for us. Our modern slaves, as I said before, they eat energy. And the energy they eat is basically fossil fuels. And fossil fuels, they share two characteristics. You have stocks that are given once and for all, because it takes 300 million years to, in quotes, manufacture coal from ancient plants. And they emit CO2 in various quantities, depending on the fossil fuel you're looking at, but as they are residues of ancient life, they all contain carbon, and when you burn them, they all emit CO2. Okay? You cannot escape that basic chemistry. So 80% of the energy we use on Earth are fossil, remaining of ancient life. And so they come from stocks, given once and for all, and they emit CO2. When you look at final energy, I will explain after the difference between primary energy and final energy, you also see that fossil fuels dominate. Final energy is the energy that you put into a machine. Primary energy is the energy that you get from the environment. Between the two, you have the energy system. Again, I'll come back at the end. And you see that in the final energy, the share of the things that get the journalist very excited is seldom worth the paper required to print things on it. This is the increase of the energy consumption in the world from 2000 to 2014. So it's the difference between what the energy consumption in 2014 and in 2000 was, or is, sorry, for the various energies that you have on the graph. What you can see is the energy that rose the most, and by far is coal. So if the paper respected what happened during the last 14 years, for one article on solar energy, you should have 35 articles on coal. That's what you should have in the paper. Okay. So coal is the energy that rose the most. Then gas, then oil, and if you remain in renewable energies, biomass and hydro are the ones that have risen the most and by far. Okay. The reason why the press is more keen to say things about solar and wind is basically because you have more press releases regarding solar and wind. And the main driver of the number of articles that you will find in the paper is the number of press releases, basically. The other kind of thing that you can find in the press, which is a big fat lie, for example, is this. You might have found this here, I don't know. In France, you find it all the time. Okay. Well, that would be true if the world electricity was zero carbon. Here's how the world electricity is produced. This graph shows you the world electric production from 1980 till today. In 1980, as you can see, the electricity production in the world was about 7,000 billion kilowatt hours, okay, or terawatt hours. To give you an element of comparison, in 1945, the electricity production in the world was about 600 terawatt hours, which is roughly the electricity production of France today. In 1945. So electricity is by excellence, with oil, one of the two energies of the second part of the 20th century. Before, it did not exist, basically. So things that you do today as you breathe, just as I do today as I breathe, so naturally. Actually, they did not exist a century ago. Did not exist. Today, the world electricity production is over 20,000 billion kilowatt hours. And you can see that the first contribution to that total is coal. Coal accounts for 40% of the electricity production in the world, followed by gas, which accounts for more than 20%. You still have some oil, because it's used to regulate the equilibrium on the grid. And the first renewable electricity by far in the world comes from hydro. Actually, up to a very recent period, I don't know, 2 to 3 years ago, hydroelectricity was also collecting the first amount of investment in the world before wind and solar. Up there is what, and you can't even see solar on this graph. It's stuck between wind and biogas here. Okay. My belief is that we better count on something else to save us. This tremendous amount of energy that has been poured into the economic system for the last 2 centuries has massively distorted the way people work. And actually, the social structure today and the structure of work today is basically a result of that energy increase over the last 2 centuries. This diagram I'm going to show you is for France, but basically UK has gone the same way. And every Western country has gone the same way. What does the average French perform for his work 2 centuries ago? He's a peasant. Okay, what you can see on this graph is that 2/3 of the active population 2 centuries ago basically worked to produce food. And the productivity of a farmer or peasant at the time was sufficient to feed himself or herself, not very well, by the way, and 0.5 person that was doing something else. That was all we were able to do at the time. You can see that the agricultural population rises in France until 1850. The reason to that is that until 1850 we are still clearing forests in France to increase land which is cultivated. I don't know when is the minimum forest cover in Great Britain, but I would suggest it's not very far from, maybe it's a little bit earlier. So the population in agriculture increases. Then it's going to begin to decrease. Why is that? Because the amount of fields is then fixed. And the rising industry pours in more and more efficient tools manufactured by the rising industry. So the productivity per peasant is going to increase, and it's going to increase sufficiently so that at the same time the peasant required in the fields decrease, and the productivity per peasant increases enough to feed a rising population which is employed elsewhere. Then after the World War II, machines come directly into the fields in the form of tractors, and at the same time huge machines named refineries, then industries help peasants to become so productive that one peasant of today replaces several hundreds of peasants of the time, which enables you to eat meat at every meal, or almost. What does the rest of the population do at the time? Well, we have plenty of energy everywhere, so not only in the fields, but in the mines. So we are able to extract more and more resources from the crust of the planet. We progressively extract all the table of Mendeleev, transform all this table of Mendeleev into the 100,000 objects that now surround us. So we need more and more people to do this. And actually, the jobs that are created are servants of machines. Servants of machines. A worker in a factory is a servant of a machine. No machine, no job. During that period, the energy supply per capita rises faster than the average size of the machine. So we're able to create more and more jobs into factories. Then comes the oil shock. The energy supply per capita stops rising, but the average size of the machine goes on rising. So the number of jobs in the industry decreases. Doesn't mean that the industrial output decreases. Actually, you will see later, the industrial output has gone on rising until 2007. But it means that the number of servants of machines that we need into the industry decreases. Less and less jobs. But the industrial production still rises. So we need more and more people to manage, sell, finance, compute, account, etc., teach. So we have this increasing amount of people that got poured into the service part of the economy. And at the same time, we also witness a new category that appears, which are people that have a place nowhere. They have a place nowhere because the productivity per people at work has become such in a box that hasn't changed its size that there is not room for everyone who wants to work. There are only two ways to escape this problem. Like France, growing number of unemployed people because you have a minimum wage. Like UK or Sweden, no minimum wage, working force. Only two, or US. You have only two ways. Comes from the energy issue. So what I've told you so far is that we have plenty of resources. They are all free, including oil, gas, and coal. They are free. Nobody paid a cent or a penny in this room for these resources to appear. They are free as the wind and the sun. All of them. All of them. They burn. They enabled us to have machines and chemistry. Machines and chemistry allowed us to transform all the rest that we find on Earth. And it enabled us to have the social system that we have today with only 40 hours of work in a week, with retirement, with long studies, with holidays, with mobility, with a home for everyone, with etc., 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 etc. All comes from energy. All. Two questions. First one, how long is the flow of energy coming from the crust going to rise? Second question, what do we do with the waste of this energy use, which is CO2 that we put into the atmosphere? And in between, we have a holy GDP. Couple conclusions on the first one. When you draw from a stock, which is given once and for all, be it copper, iron, oil, coal, diamonds, whatever, well, you cannot have an ever-growing yearly extraction coming from that stock. This is totally impossible, otherwise your stock is infinite. You cannot even have a constant drawing from that stock every year, forever. All that maths allow in such a case is that if you go back sufficiently in time, the extraction will be zero. If you go forward for a sufficient time, the extraction will be zero again. And in between, you will go through a maximum. So for any stock, which is given once and for all, we'll have something called the peak. It's going to be true for oil, sorry, the case for oil actually. It's going to be true for gas, true for coal, true for uranium, true for copper, true for nickel, true for tin, true for cobalt, true for vanadium, true for diamond, whatever, just name it. If you have a stock which is given once and for all in the Earth's crust, the general shape of the extraction over time is going to be the same. The only good questions are when at the latest, at what level at most, and is it serious or we just don't care? Okay? These are the good three questions. Any peak is particularly easy to forecast if it's already passed, which is the case for oil and gas discoveries. Oil and gas discoveries have peaked about 50 years ago, which allows to say that the amount of recoverable oil and gas on Earth, we know it approximately. It's not exact, okay? Approximately. So we have the possibility to derive the approximate profile of the extraction of this oil and gas. And for oil, here is the general shape of extraction coming from sufficiently back in time, actually a little before the beginning of the 20th century, till the end of the 21st century. And the blue line shows where we are today. So basically, we are at the peak. And if it was not last week, it's going to be in 5 years. Actually, it's an undulating plateau. I can go back to this if there are questions. What you probably know, at least for the distinguished engineers that are here in this room, is that when you are at the peak, the increase becomes nil. The derivate is nil at the maximum, as you know, or as you recall. So something which might be interesting to look at is the rate of growth of the oil extraction. Here you have the rate of growth of the oil extraction for the last century and a half. A century and a half with very primitive means. We could grow the oil extraction by 15% per year. Then with more sophisticated means, it went down to 10%. Then with even more sophisticated means, it went down to 5%. And today, with very sophisticated means, we are close to zero. So we are nearing the maximum. By the way, shale oil and gas, well, shale gas, sorry, not shale oil. Shale gas has been known for 2 centuries. The first commercial extraction of shale gas in the States was in 1826 in Fredonia on the eastern coast. So it's not something which is brand new with brand new technology. It's back to the future. It's back to the future, shale gas. The first thing that comes to the mind when you look at this is, my gosh, how much am I going to pay oil? Well, the good answer is you don't know, and I don't know, and nobody knows. Here in red, you have what has been the price of oil for the last 20 years, since 1985, and all the colored lines are the projections that have been made by the International Energy Agency. Just put it to the bin and save time. The good answer is that you have no link. Tough luck. On this graph, you have from 1921 to today, on the horizontal axis, the world oil consumption, and on the vertical axis, the price per barrel, in constant dollars. And what you can see is that you do not have a pattern that would resemble this, which would be logical if you consume more oil if the price decreases and you consume less oil if the price increases. You should see something like this. Actually, you do not see that at all. You see that for 50 years, the volume has tremendously increased with the price not changing. Then we had the oil shocks when the volume almost not changed and the price did anything. Then we had again a period of time during which the volume increased and the price remained almost constant. And then since the early 2000s, the price is doing whatever it wants and the volume is almost not changing. So you do not have anything that resembles a long-term elasticity in the relationship between price and volume regarding oil. So even though you are able to tell me how much oil we are going to consume in 15 years, you will never be able to derive a price from that. Never. The second thing for which price is not the issue is that there is no link between the oil price and the world GDP. Same thing. If the GDP were to decrease when the price increases and vice versa, dots should be organized along such a pattern. What you see, again, is not the case. When you look at the world GDP against the price of the barrel, you see that the GDP can increase with a decreasing price, increase with an increasing price, increase with a decreasing price, increase with an increasing price. So for the world GDP, the good answer is you just don't care about the oil price. You do care about the oil price for importers. You don't care for the world GDP. You do care about volumes, though. And tough luck for us, Europeans, volumes are decreasing. This is the volume of oil consumed in Europe. It's the total of oil produced in the North Sea. You Britons are very well placed to know that it's decreasing. And in green, you have the imports from outside the world. This is 2006. In 2006, the oil consumption in Europe began to sharply decrease, and it is not because we have wanted it. It is just because we could not compensate with imports the decrease of the North Sea, and we could not compensate with imports because from 2005, the world production of oil in energy terms is about constant. And the shale oil boom in the US has basically offset the decline elsewhere in the world. Basically. It's a little bit over, basically. So we have a world issue on oil, and this is going to continue. Okay, we are not finished with the decline in oil supply. Now gas. Gas is a regional energy. The North Sea is providing 60% of our gas. The North Sea has begun its decline in 2005. And the imports, basically, they add something which is constant in volume. And so the overall gas supply declines also. This is my personal estimates of what we could get in Europe from shale gas if we decided to dig holes everywhere, which will probably not happen because we are not, as in the US, we are not an empty country. And so this is the European energy supply. As you see, oil decreases because of geological constraint, gas decreases because of regional geological constraints, coal decreases because of a declining production in Europe that began before climate change was a concern. Nuclear presently decreases because a number of people are frightened by nuclear, and new renewable energy is already beginning to slow down, and that's normal. It's because equity requirements for new renewable energy are massively superior to what they are for any other form of energy. I will go back to that when there are questions. This is 2006. Now look at the industrial production in various European countries. This is European Union as a whole, began to decrease in 2007. This is what I mentioned just previously. The industrial output did not begin to decrease when the fraction of workers in the industry began to decrease. Because you don't care about the number of workers, you care about the number of machines that can work. If you have less energy, less machines can work, even though you have plenty of machines, and so you have an industrial output that declines. And it declines everywhere. So it declines in France, but that's because we have lousy politicians. But it also declines in Great Britain, but that's because the city wants to be the master. No, sorry. Declines in Denmark. Declines in Sweden. Declines in Finland. The Germans are the European champions. Does not decline. It remains constant. Declines in Spain. Declines in Italy. Declines in Japan, by the way, and it declined in the US before the shale boom. And the only reason why it recovers in the US is because of the extra energy supply of the shale boom. If you look at the trend over 50 years, you see exactly as for oil, the rate of increase of the energy consumption in Europe is declining, which means that in mathematical terms, the second derivative of the energy consumption is negative, or has been negative for 50 years. And the first derivative went through zero a couple of years ago, and now we're entering a world of decline in the energy supply. So we are probably entering a world in decline of the GDP. This is the growth rate of the GDP in Europe for the last 50 years. And as you can see, up, then down, 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 down. We're closing zero. And actually, I didn't have the time today, but if you look, if you corrected the GDP for stock inflation, real estate inflation, and creation of debt, we would already be in structural recession. Already. We'll have to live with it. This is OECD, and this is the world. Basically, you see the line doesn't cross the horizontal axis at the same time, but the trend is the same everywhere. Now, a couple elements on the downstream issue. This little joke is to remind that regarding climate change, there has been a hot, so to say, debate on the fact that we should not mix a correlation with a cause-to-consequence relation. Okay? Because when we do this, sometimes we can end up with conclusions. Exactly. The good ones. I'm going to show you basically just two things. First one is this one. You all have in mind that what is at risk or what is at stake regarding climate change is a couple of degrees increase of the average Earth temperature. When I say this, it doesn't give you a clue on whether it is serious or not. To give you a clue on whether it is serious or not, you have to confront that increase to past temperature changes in the ancient times to know whether it represents something massive or not. So what I'm going to show you today is the difference between present Europe and ancient Europe. This is present Europe. This is the ecosystems that you can find in Europe if you leave them alone and do not clear them to build universities, fields, railways, etc. As you can see, it's forest everywhere, except very up north, where it's too dry and too cold to have forest, and far east, where it is too dry to have forest. This is the world 20,000 years ago. As you probably know, 20,000 years ago, sorry, we were at the last glacial maximum. We were in the course of the last ice age, and we were at the point where the average Earth temperature was the coldest of the last 100,000 years. Obviously, the landscape is not at all the same. As you can see, you have no students in UCL, if you have some today, coming from Scandinavia, because Scandinavia is buried under 3 kilometers of ice. So that's good news from students coming from the rest of the world. No competition to fear with Swedes, Danish, and Finnish. They do not exist. Good news for the referendum from, that regards Scotland. There is no need to have a referendum. They are buried under the ice. Okay. You can see that the coastline goes outside what is presently Great Britain, and there is a very bad piece of news for you. You are the same country than France. No channel. Okay? The lowest part of the channel is at 114 meters. And the ocean has decreased by 120 meters at the time. All the water that is not in the ocean anymore has gone into these tremendous ice caps that you have on Scandinavia and on Canada. What you can see also is that the ecosystems that you find in Europe at the time are ecosystems that thrive, so to say, in dry and cold places, just like the northern part of Siberia today. In France, Great Britain is even less. This ecosystem of the time is able to feed about 100,000 people. 100,000 people is all France is able to feed at the time. Soil is frozen all year round, okay? No forest, 100,000 people. Well, the average temperature between these two landscapes has warmed by only 5 degrees. So when you warm the Earth by 5 degrees in 5,000 years, that's the result you get. Now just picture, we perform the same increase in 1 or 2 centuries. What we will get is not the occasion to put on our swimming suits 15 days earlier or 1 month earlier. We'll basically get war everywhere. That's basically what we'll get. We'll get war everywhere. Because the competition for resources and the ability to move and settle in some place where we can thrive again is nil. At the time, 20,000 years ago, moving was easy. The head of the tribe would take his mass, strike everybody disagreeing with him, grab all the other people by the hair, and move to the next cave with a set of colors to paint the cave, 3 harpoons, 2 axes, and that was it. That was moving at the time. Okay. Today, moving is not exactly the same story. I mean, you don't picture the British or the French putting on their back their churches, their streets, their factories, their schools, their universities, all the infrastructure that we have set up for the 2 centuries, or even more, that the harbors, etc. We're not going to put all this on our backs and move to some other place. Because first of all, we cannot move with all this. Second, at some other place, either it's something which is not which is nice, and there is already someone living there. Generally, it's not going to agree with the idea of seeing hundreds of million people coming where it lives. And 2, if it's a place where nobody lives, there is no infrastructure. Okay. So it's not going to be smooth and nice. It's going to be something brutal and a turmoil. Now, the type of consequences that we can have in this rapidly moving world is going to be a mixture of decreasing agricultural yields, dying ecosystems, changing diseases, you don't know exactly how, increasing extremes, rising ocean, increasingly acid ocean, changing of the ocean or returning, increasing of the extreme events because, well, the unitary power, unitary energy released by an extreme event is going to increase. A melting that has already begun for Greenland and a part of Antarctica, the western part. The soil that can turn into a carbon emitter. And of course, this is going to exert pressures on human societies directly, but mostly with ways that you cannot imagine, and I cannot imagine either. Because when you perform an experiment for the first time at such a scale, it is just impossible to figure out all the possible outcomes. Take an experiment that humanity has performed 5 billion times, which is wedding. 5 billion times, also. Okay. Well, take a newly wed couple today. You're just not able to say what they will become in 4 years' time. For an experiment that we have done 5 billion times. So you can easily imagine that this experiment that we are doing for the first time is basically leading us in an unknown world. And in the unknown world, something which is very simple to understand is that as time passes by, we will get more and more surprises. And the difficulty is that a large part of these surprises, we won't even understand at the beginning that it's coming from climate change. Now, if we don't want, well, if we don't want, it's very simple. It happens that the climate temperature change and all that follows is basically a function of the accumulated emissions that we'll have. With the accumulated emissions that happened so far, we know that we already have a degree and something. And if we want to limitate the temperature rise to 2 degrees, then all we can emit extra is half the past emissions. Okay? And then mathematics are very simple to perform. If we want to limitate the future emissions to half the past emissions, we have to follow the bottom black line. And so emissions must be divided by 3 by 2050. By 3. In 35 years time. I'm running out of time, so I know I cannot go on, but a rule of 3 can show you that we will not match this challenge, will not meet this challenge, sorry, with only technical measures. We'll never do it. So basically, the choice that lies in front of us is either we manage, which is not easy in democracies, to voluntarily decrease our consumption, which bears the awful name of recession or the awful name of sobriety, or we wait as long as we can before a collection of unwanted events performs the same thing for us. This is basically the choice we're in front of. And I will end here.
Well, a lot of ground, starting here in about 1750 and all the way through to the end of the current century, painting a very interesting picture. Those of you who are younger than me, I'm sure will find the next few decades interesting. Whether you find them comfortable or not is an entirely simple question. So, questions and answers. Who would like to put the first question? Could you just put the record, could you give your name when you speak, please?
高島津田京都 University European Centers. Thank you very much for the very impressive and intuitive lectures. As I understand, the 200 years progress is going down within these 10 years. And
Sorry, I didn't understand. What is going down?
Some economic figures is going down. So it's for me the very nice economic talk. So, but for our generation, the going up and down and a foresight for going down is very, very serious. But for you, it looks for me, it looks enjoying and very, very optimistic. Do you have any secret why you can talk so optimistically?
Because being optimistic or pessimistic is a matter of genes and not at all a matter of the situation you're looking at. I mean, basically the optimists are those that want to fight, and the pessimists are those that want to sit and wait. And you can find these two types in whatever situation there is. It doesn't mean, well, in other words, I think that significant changes await us, but I don't see there a reason to sit and cry all day.
So I recall a man called Peter Chapman saying that if policy were designed by pessimists, then the outcome might be quite optimistic. And if policy were designed by optimists, then probably not. Yes, please.
Ken Neal, I'm a building design environmental consultant. I've read recently a UK government report which says that unless we drastically change the direction of our economy by 2040, or the world economy, sorry, by 2040, it will collapse anyway. Unless we drastically change direction now, it will collapse by 2040.
I'm going to be very rude. You're probably old enough, as I am, to remember the Club of Rome and the work by Meadows. Does it ring a bell for the people in the audience? No? Dennis Meadows was a physicist, I think, of the MIT, who specialized in system dynamics. And at the age of 30-something, not much, he co-authored a book named The Limits to Growth, which summarized some work he had performed with some colleagues at the MIT, and he did what is, in my view, the best economic model that you can do, because it associated the physical flows that are necessary for the economy to exist with the economic outputs and with the size of the population, etc. And it was a simple model that Meadows calibrated on the past data. And then he looked at the model and looked at what it could yield in the coming century. And the conclusion of Meadows was very simple. It was, if we do look forever, or for as long as possible, to be more precise, for perpetual growth, then in the course of the 21st century, the system will collapse. And it will collapse because of overshoot, meaning you will have hit so hard into the natural boundaries of the planet Earth that it will not be able, the system will not be able to sustain a growing humanity or even a constant humanity. The system will collapse and we will witness an unwanted decrease in population size, agricultural output, industrial output, etc. A couple of years ago, an Australian researcher at the acronym is CSIRO, I don't know, CIRO, is that what you?
Something like
that. Looked at the outputs of the model and looked at the way it matched or not the tracks that we followed since then. Pretty well matches. So basically, we're still on track for something very unpleasant happening before you die and my kids die. Obviously. So it's what I just said. The choice that lies in front of us, and it's a difficult choice because democracies are not equipped to face long-term challenges. It's either we find a way to combine some kind of material restriction with some kind of optimism. So we just say, I don't care, because I've got something to do and I'm pleased with that. Or we will probably have some kind of unwanted regulation. And you know that regarding the size of the population, the unwanted regulations are not very numerous. Hunger, disease, war.
Okay, I'll take Nicholas Taylor. You talk about us and the democracies. Are you most optimistic about the fate of the democracies developed countries, or about the new underdeveloped or developing economies?
I'm sorry, I'm not sure I got the question.
Are you most optimistic about the existing countries or the new large developing countries? Because you only mentioned us as democracies.
I'm not sure I have a conclusion on that point. What I'm sure of is that democracies are a slow and uncertain system. It's a try and error system, democracy. When you are facing a direct challenge and you need drastic answers implemented within a short period of time, a democracy is not the most convenient system. And I say that in a country which remained a democracy through the last World War. You have two exceptions of countries that remained democracies during the last World War, but it happens that both of them were not invaded. I don't know what it would have, what fate would have been yours in the other case. And at that time, the danger was crystal clear. It had a name. You could see the thing that you had to fight, and so it was pretty easy to mobilize everyone and to ask them a huge effort. Here, we're in front of some kind of invisible enemy. I mean, the enemy lies within a construction. It took me 1 hour to show it to you, and it's incomplete. But during a war, it takes you 1 second to see the enemy. Has a uniform, has a helmet. I mean, it's very simple. There, it's a construction that you have to believe in, and it takes 1 hour. So that's the challenge for me. It's basically doing the maximum in front of an invisible enemy. And democracies, obviously, is not something which is very suited for that kind of task. So my fear, and it's a fear, it's not a wish, my fear is that democracies do not resist the unwanted regulation.
If you could be the supreme world leader, what would you actually do?
Well, first get rid of my neighbors, and then we can discuss all the rest.
So, you thought about this?
I'm very serious now, son. You have to imagine the best compromise between what can be left of our material consumption and what has to be done in order to implement something which is reasonably sustainable. The ingredients that you will find in that general frame includes a soft decrease of the population. That's a soft. We don't like wars. But obviously we'd be better off on this planet if we were 1 billion or 2 instead of 9. You need slowdown of the general flows, which means that the economic activity shifts back to a higher proportion of things done slowly, locally, and fully. So you have smaller productive units, more polyvalent, and then with production prices, the costs are decreased, more fixing, less manufacturing, lower technology, which might be surprising to you because you're not able to recycle a product in which you mixed 2/3 of the table of Mendeleev, just impossible. A lower cost of capital, a long-term investment, a higher fraction of the work that goes to infrastructure adaptation or change, a higher proportion of work that involves, again, some kind of manual work, and a decrease of the office work. Quite surprising, because many people figure that in a world which is dematerialized, we'll all go to the office and get out of the office, you know, with no spot on the trousers. Or actually, I believe it's going to be exactly the opposite. A maximum efficiency, but some kind of organized sobriety, which is already happening. If I may suggest you 3 definitions. When you look at energy savings, there are 3 things that we mix all the time. It's efficiency. Efficiency is I get the same service, but the brilliant engineers in the room have made so that it consumes less energy. So I live in the same housing space. I drive the same car, but it uses less energy. That's efficiency. Sobriety is a decrease of the energy consumption through a willing decrease of the services and goods that I consume. I live in less housing space. I drive less or a smaller car. I buy less goods. And I do it willingly. Poverty is the same thing, only I don't want it. Okay? I give you these 3 definitions because it seems to me that they are important to say what we're discussing precisely. So, maximum efficiency, but we won't do it without sobriety. And sobriety goes along with an economic regulation. So we should, somewhere or another, put what is generally called a higher price, but it can be a higher invisible price. For example, if you say that in Europe, in 10 years' time, it's forbidden to sell a car that uses more than 2 liters of fuel per 100 kilometers, that's an invisible price. It's not an explicit price because it goes through a regulation. But it's among the things that we should do. So basically, we should organize the sobriety the best we can. We should increase the efficiency the most we can. We should suggest projects so that people don't care the most we can about decreasing their consumption. We should decrease the size of cities because a city of 10 million people is not sustainable with decreasing energy flows, whether it is sprawled or dense, doesn't matter, because it needs routes that go so far to live for food, products, etc., that whether it is dense or sprawled, if it's 10 million people, cannot survive in a world of scarce energy. Cannot survive. We should put more added value in the in the rural areas. So more people farming are transforming things from the farm. So it's pretty easy to describe. The difficulty is that it's very easy to describe actually. It's easy to convince people that it's the best buy in today's world. And the main difficulty lies there. It's that a significant fraction, at least as long as we remain in democracies, 50% plus one of the voters consider that it's the best buy or the least worst, if I can use that expression.
How about moving to somewhere 20
You're
metres
cheating.
above sea
There
level?
was somebody wanting to ask a question.
Okay. I'll take Paul. Yep.
Paul Roosevelt, UCL-Energy Institute. Given the problem with democracies, which I entirely agree with, what's the role for global corporations in this future scenario, particularly if they can be enlightened?
They occupy, for me, a very interesting position because it is multinational, non-democratic institutions. So they have the possibility to act over a single country. And if the boss has decided within the legal frame that people should go this way, if you don't obey, you're fired. So they are probably part of the solution. When I say they, I should be more precise. Some of them are part of the solution. Some of them are part of the problem. But one of the things that I'm trying to achieve in France with the SHIP project, and actually it's already crossing the borders a little bit, is precisely to create the lobby of all the large corporations that will benefit from a constraint put on fossil fuels. Because you have in democracies to have a lobby behind you if you want to be heard. As long as all you have to be heard is rules of three and your brains, you're no one. You're just no one. It doesn't count. What counts is when you have a significant number of people who say, whether their reasons are good or bad, I want this. And so some large corporations are very interesting I would say, to drag along. And to name them, it's corporations that are in part of the construction sector, all those that can refurbish, some people that manufacture some construction materials, particularly insulation materials, double glazing, etc. Some people that manufacture heating devices, heat pumps, for example. Some people that manufacture very small cars or bikes or etc. People that manufacture buses, because one of the very efficient ways to replace cars is not by trades in the suburbs, it's by buses. When you put somebody who drives alone in a bus, you divide the oil consumption by 6 for his daily commuting. And in France, commuting to work is 1/3 of the total mileage in cars in a year. You can drag along people that produce, of course, low carbon electricity, but you can also drag along people that produce stoves in a country like France or Austria or Switzerland or Sweden, etc. So I'm not going to name them all, but I mean the idea is that you can drag along a number of corporations that will benefit from the constraint, and then it should better. Again, I mean some lose, some win. Those that can lose have to shout louder than those that will. Some that will win, sorry, have to shout louder than those that will win. The difficulty, we know it since Machiavelli. We know that those that are about to lose know who they are because they have thrived with the existing rules. So the next day you're changing the rules, they are in your office and they protest. Those who will win, they don't all know that they will win. So they are not that well organized. Some of them are future, and so you cannot hear them shouting as loud, which is the difficulty. But basically, one of the places to look for something regarding this issue is definitely into some large economic organizations.
I'll take one more question.
Just Jürgen Huber, Germany. It's very interesting.
Could you say who you are and speak up, please? Thank
Jürgen Huber, Germany. Just got a question regarding, you showed the graph earlier on the GDP of various European countries. and Germany was doing quite well over the last few years. Can you see connection between renewable energy and GDP not going quite down?
There is absolutely no connection. I've looked at it. There is absolutely no connection. The reason why is that Germany has an industry which has specialized in exports of industrial machinery, and its exports has been pulled by the rising demand in a number of countries. So it's the reason why is that Germany is a net exporter and a significant net exporter, which was not the case of a number of European countries in the past years. And Germany has a need for domestic spendings, which is also lower than other European countries because of a decreasing population. So there is less need to build new housing, less need to build new anything, new schools, new whatever. As you probably know also, Germany is spending less into its infrastructure than other European countries. Germany has not the burden of a significant military budget, which is also something which is reasonably unproductive regarding the export. So basically it has nothing to do with renewable energies. It's linked to a number of other things. The renewable energy boom in Germany basically has replaced nuclear by renewables, or part of nuclear by renewables plus exports, basically electricity exports. So what Germany has done over the last 10 years, well, mostly 10 years, I mean it began before, mostly 10 years, is that it has increased the share of renewables into its electricity from 4% to 22%. And actually this has two components. The electricity production itself increased by 8 to 10%, and the surplus is basically being exported. So on the European market, it's not a joke now. The price of electricity really depends on the wind. I did not show it tonight, but if you plot the price of the megawatt hour on the electricity market and the wind production in Germany, you get something with a very high correlation ratio, very high. So the half of it is exported, and the other half has replaced 8 or 9 gigawatts of nuclear that has been decommissioned. But it's an internal recycling, I would say. So it doesn't push up or down the exports. So the fundamental reasons why Germany has had such an industrial output, mainly constant, is for reasons that are not linked at all to the energy vendor.
Thank you.
Well, I think we should probably bring it to a close there. I'd like to give a big round of applause, please, to our